Great pleasure to introduce David Damanik from Rice University, who will talk to us about pure point spectrum in the regime of zero Lyapunov exponents.
Okay, thank you very much. Good morning. Well, thank you to the organizers for putting together this very interesting workshop and also for giving me the opportunity to speak here. So I will talk about joint work with Anton Gurudetsky. And so basically, the goal is the following. So it's actually nice because it sort of it covers all the aspects of this program. Well, I mean, in very simple ways, but it really does. So to to use randomness so here you have randomness to generate periodic approximations of almost periodic potentials. So okay, well, so far nothing very impressive, but the point is that I can say something about these potential that could be interesting. So with surprising spectral properties. Okay, so I will start off by describing the context, then I will describe the motivation for our work, then I'll describe some of the results, and if there's time left, I'll explain some steps in the proof. So here's the context, and I know that some of you were here in January, and so basically the context is given by what I talked about in the mini course in January, so let me just recall what that is. It's really, so I'm working in one dimension, but in one dimension it's basically this framework of ergodic Schrödinger operators. So it's sort of convenient because it encompasses the three main types of potentials that we're interested in here, periodic, almost periodic, and random. It shows some common features and structures, and so it really, those common features and structures should be discussed in this context. So you start off with, say, a probability space. Then you have some transformation. So it should be invertible and should be measurable. The inverse should be measurable. And so you have some function that sends omega to R. Also measurable and, say, bounded for simplicity. And then you set V omega, which you view as a potential, to be f of t to the n omega, where omega is in omega and n is in z. Okay, so those are your potentials. And the operators will be the discrete Schrödinger operators with these potentials. So h omega will be the discrete Gaussian plus this multiplication operator, so it's this. In L2 of z. Okay, so those are the operators. And so you need one additional piece of information for this to be useful. Namely, you need the triple omega mu t to be ergodic. So that means that, well, the measure is invariant under t, and invariant sets are trivial in the sense of having zero or full measure. And so then you have a number of ergodic theorems, and you can use them to show some of the fundamental results. And so one of the fundamental results is that the spectrum of the operator h omega is actually omega independent mu almost surely. So, so this is one of the important results. And another important thing that you should do in this one-dimensional setting is to look at Lyapunov exponents. So in principle, you're interested in studying this difference equation here. And you reformulate that by passing to vectors and matrices. Okay, so this equation is equivalent to this one. But then when you look at this, if you iterate that, then you can express your solution at site n in terms of your solution at the origin in terms of, well, this matrix product that builds up when you iterate applied to your initial condition at the origin. And so this matrix product, so this is A, E, say, t to the n omega. This matrix product actually has a norm which grows at the same rate on an exponential scale, mu almost surely. So the following thing, the limit as n goes to infinity, 1 over n log. So I will denote it like this. So this product that builds up here is exactly this one. And so you denote it by A, E, n omega. You look at its norm, you ask, is it roughly of the size E to the n times something? And the something you try to identify. And so this, again, holds mu almost surely. Okay. Of course, you have to be a little careful. This full measure set on which it holds is E-dependent, so that's actually important to keep in mind, but that's just what it is. And so the other really important result is the following. So you want to decompose the real energies. So E here, I mean, is most interesting in R. So you want to decompose the real line into 3 sets. First of all, you look at this expression. You note that the determinant is 1. Therefore, the norm is at least 1. Therefore, the log is at least 0, and L is at least 0. So it's 0 or positive. Okay, so this is the first decomposition you get. But this is not really the point. The point is to decompose the second set further. So like this. Well, so I will call this here Z, and then NUH and UH for non-uniformly hyperbolic and uniformly hyperbolic. And so uniform hyperbolicity means that you have uniform exponential growth here. Right, so if you have positive exponents, then at least in an average sense, this grows exponentially, like e to the n L with a positive L. But uniform hyperbolicity, actually, this should be like this. So this here really means that there exists C and lambda greater than 0, or gamma, say, as such that for every omega, so this is the uniform aspect, so those are the E's, for which not only do you have exponential growth, but uniform exponential growth. So for every omega and n, A, E, n omega is greater than C, E, gamma, n. Absolute n. Okay, so you grow uniformly exponentially, and that's uniform hyperbolicity. And so this is just the complement of this set and that set. So here you have positive exponents, but the growth is not uniform. So under quite general assumptions, this here, so first of all, of course, the union by definition is disjoint. This here is actually equal to that set sigma, that common spectrum. Okay, so you want to view sigma as the disjoint union of zero exponents and non-uniformly hyperbolic behavior. So this is Johnson. And this is useful if you're interested in the spectral type of your operators. So here are your operators. You would like to know, whether there's pure point spectrum, singular continuous spectrum, AC spectrum. So not only is the spectrum almost surely the same, that's the same statement is true for the spectral type, And so you can relate the spectral type usually to this decomposition. And so this is really what this talk is about, to sort of explore how far you can take that. And so we have these two sets. So sigma is the disjoint union of these two sets. And here, you have no AC spectrum. So, I mean, yes?
Can I get the question that probably I forgot something. The C is not random for the euro.
The C, no. This holds for all omegas. So C is chosen before you vary omega.
So yeah, now I know you wrote this way.
Yeah, but it's...
Gamma is the Lyapunov exponent, I mean, so that you know...
No, it's a bit less. Yeah, typically yes, yeah. Okay.
But there exists one C, so you don't have different uniformity hyperbolic.
No, it's exactly like I wrote. So for every E, there's an E-dependent C in gamma. So that then for all omegas and N's, you have that estimate. Yes.
David, is it really for all omegas your A is only measurable? Because there could be some stupid stuff happening, right? If you
okay, yeah, so thank you very much. Okay, so I agree. I'm all right. So as a cop out, so here, so what you can always accomplish without losing too much is without loss of generality. So omega is a compact metric space. So you can just push forward and get that. So mu is a Borel measure and so on. Okay, so thank you. That's a technicality. You can arrange for that, and then in that bigger space, or I mean the space you push forward into, it's correct. So thanks. Okay. All right. So then you ask yourself, well, looking at the spectral type of H omega, how does that relate to this decomposition? And so this is essentially truth. So this set doesn't, at least almost surely, support any absolutely continuous spectral measure, or for any state and for almost every omega and for every state, the absolutely continuous part of its spectral measure has no weight on that set. Okay, so that's true. May contain SC spectrum. Often contains point spectrum or pure point spectrum. Okay, so this is basically what you can glean from the existing results. So here, so often, well, corresponds to the AC spectrum. May contain singular continuous spectrum. And so the pure point part was absolutely unclear. So basically, the following is true. The AC spectrum is mu almost surely the same, and in fact, it's just equal to the essential closure of the set. That means that precisely when this set has positive Lebesgue measure is their AC spectrum, and it's given by the essential closure of the set. Okay. Moreover, so by presence of zero exponents on a positive measure set, you can ensure the presence of AC spectrum. Moreover, so this is also true, whenever you are in the regime of positive exponents, you really feel like you want to prove localization. I mean, that's just what people have done since the 80s, 70s maybe? I don't know. Well, anyway, if you have positive exponents, your inclination is to prove localization. Of course, it's not always technically easy, and of course, it's not always true, but that's your first inclination. Okay, so of course, there are examples known where there is SC spectrum here and SC spectrum here. However, much like in the theory of the sort of classical atomic models, excluding the presence of a singular continuous spectrum gives you a pretty nice spectral picture. In this context, really, basically, you partition the spectrum into a localized part and into some part, well, at least where you have AC spectrum, and hopefully also some good transport behavior. Okay, so this singular continuous spectrum is a nuisance, maybe there, but if you exclude it, you get a pretty good picture, except for this question here. So just from this general perspective, it's of interest to ask question, can there be eigenvalues? In Z. So that's my first question. There's a second question. And so let's go back to our setting here, maybe in this particular, yes?
You wouldn't have pure spectrum, right?
I think you can.
You can.
So I should say this is...
Isolated eigenvalue corresponding to Lyapunov exponent 0.
Yeah, I will tell you what our results are, and I will also tell you what we hope is actually true. Yeah. Yeah, so no, I think actually what the right result should be is that not only do you have pure point spectrum inside Z, but you have it actually for all omegas. So I think there is an example where sigma is equal to Z, and for all omegas you have pure point spectrum. But we can't prove that yet, unfortunately.
And how does it fit with Damanik theory?
It has zero measure.
Zero.
Okay.
Okay, so second motivation is limit periodic potentials. So as I said, this framework contains many examples. In particular, our main examples, periodic, almost periodic, and random. Limit periodic is a special case of almost periodic. So limit periodic potentials. So V bounded is limit periodic. If there exists periodic VKs, so that they converge to V in L infinity. Okay, so you can show that if you're limit periodic in the sense, then you're almost periodic in the sense that the L infinity closure of the set of translates of your potential is compact in L infinity. And then this compact closure of your set of translates is the omega you want to consider. It's called the hull. It's a compact abelian group. On it you have the Haar measure, which is mu. And you have the translation just by regular translation on these sequences. That's COT. And the F that you take there is the evaluation at the origin, and that's it. So these are limit periodic potentials, and they're interesting as a special class of almost periodic potentials, as ones that are very well approximated by periodic potentials, and therefore, because we know a lot about periodic potentials, should be relatively easy to study, and yes, they have been studied for a long time. But there was one nagging question that was left open, and so that I want to describe here. So, the following are known for, so any topological statement here, statements are in the L infinity sense. So for a dense set of limit periodic V's, H has purely AC spectrum. Okay, so phrase like this, it feels like I'm cheating because due to that definition, a periodic potential is limit periodic because it approximates itself. It has AC spectrum, and by definition, the periodic guys are dense. So to make this more interesting, you can add the other statement that not only does it have purely AC spectrum, it also has a Cantor spectrum. So that makes it aperiodic. And you can even impose properties that the Cantor spectrum has to satisfy. So this actually is an interesting result. So this is the natural thing you want to do. You have, by definition, these periodic approximations. All the periodic guys have AC spectrum. You ask, well, can I push that through to the limit? And you can for a dense set. So this is sort of the natural spectral type you want to exhibit, and it occurs densely. However, it doesn't occur very often in a topological sense in the following sense. So for a dense G delta set of limit periodic V, the operator has purely singular continuous spectrum.
Could you please repeat what is the topology?
L infinity. L infinity topology. No? Sorry?
Can you really
Uniform.
approximate by periodic any function in infinity?
No, not any.
I don't understand. Oh, so, okay. The space is the space of all limit periodic potentials.
Okay.
And within this space, there is a density delta set. No, I'm only interested in limit periodic potentials right now. Yeah. No, I think the way it's phrased, it suggests that I'm talking about the space. Okay, so great. So what about pure point spectrum? It's not really expected to occur, just, I mean, because the approximants are purely AC. So how would you arrange for a pure point limit? However, it was known there exists limit periodic V so that the operator has pure point spectrum. So this pure point spectrum comes with positive Lyapunov exponents. So in fact, they are uniformly localized. That was actually really interesting because there was this discussion in the 90s of what is localization. These notions of ULE and SULE and so on were discussed. SULE was verified for many models. ULE, uniformly localized eigenvectors, were sort of regarded as something that doesn't really occur. Was shown to not to occur for many models. However, it occurs here. So these limit periodic guys are uniformly localized. They're more localized than the Anderson model. They have uniform dynamic localization. It's really amazing. But anyway, this, I mean, it's more than an existence proof. There's a way to construct examples, but all these examples will be very large. This is a large coupling regime result. That doesn't tell you anything about a limit periodic potential of typical size, like 1. Okay, so this was known. And so the question that arose here is pure point spectrum a dense phenomenon? In the limit periodic, in the space of limit periodic potentials. There are a dense set of limit periodic potentials so that the operator has pure point spectrum. So let me phrase some of our results. So everything is from this ongoing work with Anton Grodetsky. So for, well, the theorem is yes. So for a dense set of limit periodic V's, the operator has pure point spectrum. So that answers question 2. Okay, so the way we prove it actually proves a stronger statement, which is interesting. So not only can I perturb an arbitrary limit periodic potential by an arbitrarily small limit periodic potential to turn the spectrum into a pure point, I can perturb any bounded potential. So for every bounded V and, and epsilon greater than 0, there is limit periodic such that has pure point spectrum. Okay, so this is a result that's known for random perturbations. So random, yes? Thank you. Thank you very much. Yes, so if you replace limit periodic by random, it was known. And so, I mean, it's an interesting statement, right? I mean, if you add something and something random, it doesn't matter what the something does. The random guy dominates. Randomness is so strong in one dimension that it localizes, even at small randomness, everything that you start out with. And so, I mean, this is in some sense shocking. Limit periodic potentials do the same thing. So, but it just comes out of the way we prove theorem 1. Okay. So for question 1, theorem 3, so for a dense set of LPV, you have pure point spectrum. So that's the same statement as before, but basically it's a strengthening and two things. So you have zero exponents and you have zero measure, which is of course necessary. As Christian pointed out, if it hadn't zero measure, then by Koutani theory, it would have AC spectrum, some AC spectrum, but it doesn't. It has pure point spectrum. Okay, so so this is the theorem, but to answer your question, so the point is we prove pure point spectrum for the limit periodic guy we construct, and then zero exponents for the hull. We actually think, and we will try to prove that you have pure point spectrum for every element in the hull. So that would give the result I mentioned before. We can't do that yet. It's a bit unfortunate, but it's also not so easy. We've tried, but we'll continue to try. So this is a little cheeky in the sense that I'm talking about a spectral statement for a specific operator, right? I say there is a dense set of limit periodic V's, so that for each V in this dense set, this operator has pure point spectrum. And moreover, if you take the V you're currently looking at, take its translates and orbit closure, for that hull, you have these statements. And I also think that for the hull, so all the translates, of course, but all the limits of translates, we also have pure point spectrum. So that's what we're hoping, but can't prove yet. Okay, so this addresses the two questions that I used as motivation, but then once you look at the proofs, you see that you can do more. So let me give you another application, which, so I guess, so the point is that these properties are surprising given what was known before. So I mean, before we worked on this, I wouldn't have thought that this here is true, but so I think it's surprising. But here's another statement that's surprising. So you look at quasi-periodic potentials. So theorem. Okay, so for every irrational alpha, for every epsilon, not irrational, for every epsilon greater than 0, and every omega in the circle, there exists f from the circle continuous. So I'm talking about one frequency quasi-periodic potentials here. So with f infinity norm less than epsilon and Laplace plus f n alpha plus omega. Okay, so this is the general form of a one frequency quasi-periodic potential.
What do you mean by f omega?
What do I mean by f omega?
F infinity, I'm sorry.
That's the L infinity norm.
I didn't read it correctly, I'm sorry.
Yeah, it's infinity. So it's a small. Okay. So and this guy has pure point spectrum. So this is surprising. Why? Well, for two reasons. First of all, the general philosophy is that small quasi-periodic potentials have AC spectrum, or at least a tendency to have AC spectrum. That's been confirmed under suitable regularity assumptions. And it hadn't been disproved under absence of these regularity assumptions. So there really was no result on pure point spectrum for small sampling functions in this context. So the smallness here is surprising. What is also very surprising is that there's no assumption on alpha. You can take alpha to be Liouville. And so there also have been this philosophy, well, if you have a Liouville frequency, then a Gordon lemma tells you that you have no eigenvalues. No, you can have pure point spectrum. Okay, so of course the Gordon lemma is very useful, and what it gives you is that if you assume a fixed modulus of continuity for f, then there's an associated class of Liouville numbers alpha, so that you have no eigenvalues. That's the correct statement. But here you choose alpha first and then construct f. And in particular, f will not have a very good continuity property. But it will be continuous. Okay, so that's theorem 4. And you can generalize that even more. So again, you can write on a version of theorem 4 like this. You can start with an arbitrary background. In particular, you can start with an arbitrary quasi-periodic potential and perturb it by an arbitrarily small to turn it into pure point. So therefore, the set of f's for which you have pure point spectrum is dense. And again, you can perturb any arbitrary background potential. And so on and so forth. You can replace irrational rotations by other things. It really is a very, very general result. Okay, so now that I've stated some of the theorems, there is something that's working in the background. So all the theorems are, in some sense, about almost periodic potentials. What's, of course, really going on is randomness, because, right, if you have a limit periodic potential, what you have is the following. It's periodic approximants and an almost periodic limit, neither of which by themselves will indicate anything about the existence of eigenvalues. So something you have to work with, and so you want to work with randomness. And so the the heuristic picture that I had in mind for some time, and really I've tried to, actually the history is the following. So what I'm just erasing here is basically a thesis of one of my former students, Jan Gon. And while he was working on his thesis, he worked out these things and others. I asked him, what about pure point spectrum? Can you prove that it occurs on a dense set? And he said, I tried, I can't. And I tried to, and that really was like 5 or 6 years ago, I don't know, really a long time. And the question really had been on my mind, and I had some heuristic idea how to do it that I sort of offered to anyone who wanted to listen. And so here's the picture. Okay, so here's n. And I want to construct a limit periodic potential so that the operator is pure point spectrum. Okay, so what I do is I take a random potential. Okay, a random potential will give me everything. It will give me positive Lyapunov exponents, exponential bounds for Green's functions, exponential decay of eigenvectors, and so on and so forth. So by putting something random here, I get good things that I want to work with. Of course, I can't keep going, because that will not produce a limit periodic limit. And so therefore, I have to stop at some point. Okay? So then I have this finite random piece. On this finite random piece, I'm good in some sense that I have to make quantitative. And now I take this piece and repeat it periodically. Okay, so this is my first piece. Okay, so good. Yet now I have a periodic potential. That doesn't have any eigenvectors. It does have some weak signatures of localization on this finite piece, but once the particle realizes it's in a periodic medium, it doesn't care anymore. Eventually there's ballistic transport. The eigenstate doesn't decay at all. Okay, so I have to keep going. Okay, so then I iterate that, and I add a small random perturbation. So here I use that this analog of theorem 2 was known for random potentials, namely, whatever I start with, if I add an arbitrarily small random perturbation, it will localize the system. Okay, so I add a smaller random perturbation. maybe like this. Of course, actually, I will run out of space soon. The growth of these lengths will actually be different, but okay, so I add a small random piece on top of it. Okay, so now I will have signatures of localization up to this point, but weaker. Okay, there's slower decay up to that point, more or less. But still, up to that point, it will try to generate growth of transfer matrices, decay of eigenfunctions, and so on and so forth. And then I just keep going, okay? So this here is my level k. This is my space variable n. And I just keep on adding periodic potentials whose periods are given by realization of something random. And then at some point I stop, and then I repeat periodically. Okay, so if the decay of the randomness is fast enough, summable, then of course I will produce a periodic limit in this way, just by construction.
What do you start
I start with a random variable, okay, and then I determine the value here. Then I take the same distribution and independently determine this value here, and so on and so forth. And then I've determined these numbers. And then I repeat them periodically. Full stop. Then I take a break. Now I take a deep breath and do it again. Take a different distribution, but smaller randomness, and determine this number, and independently determine the other numbers, and then stop, and repeat periodically. Okay? So the randomness here has to decay in a summable way, so that these periodic sequences add up to something that converges, yes?
The phrasing here is that it's weaker, but the sequence is longer.
Yes, it's exactly about the right choice of this interplay between periods and size of randomness.
Somehow you want the total variation of the function will be still significant, right? I mean,
Yeah, so I mean that's the idea. Okay, so I mean of course the construction has to do that. Randomness enters the game by producing something that you can exploit up to a certain point, and then you have to ignore it basically. Then you use this here, right? And then you take a much smaller random piece which you then repeat, and so on. So right here, V will be the sum k from 1 to infinity of vk's. So this here is v1, v2, v3, and so on. So that's the construction. But the question is, can you make it work? So, of course, I mean, just by writing down, by drawing this picture, you think there might be something there, but how do you implement that? So the challenge, actually, I mean, there are quite a few challenges, but for me, the primary challenge is the following. So even if I can't prove all the estimates on the transfer matrices, like I will get growth here, and I will get growth here, and again, and again, and again, the rate of exponential decay, of course, will decrease because randomness decreases. It's known that the small coupling limit of the Lyapunov exponent for random potentials in one dimension is coupling squared. So the Lyapunov exponent that I can sort of extract from these random pieces will go to 0 as I move out in space. So that's clear. So if this works at all, it's sort of clear that I only can produce sub-exponential decay. Growth for matrices, decay for eigenfunctions. But the big question is, I mean, everyone who's worked on localization knows that, well, especially in one dimension, because the methods are just like that there, if you get the right behavior at infinity, at the two infinities, you still have to match them at the origin. So that's a major issue here. So even if you get a good growth here, and by an oscillated type thing, good decay on eigenvectors, well, fine. Then you get these decaying eigenvectors, and so the question is what happens here? Of course, there are a number of ways of dealing with that. Spectral averaging, multi-scale analysis, many different ways, but none of them obviously work here. Spectral averaging is really a problem because, well, you would want to wiggle randomness at the origin, but by construction, that wiggles the potential everywhere. And you lose the control because at some point, you actually have to pick realizations. And right, you can't just wiggle at one site. That destroys limit periodicity. To keep limit periodicity, you have to replicate that. Multi-scale analysis is really not obvious to implement here. So in any event, there's a question. And so what comes to the rescue and actually is responsible for these extensions of the results is that luckily in one dimension there is a way of proving well, localization or pure point spectrum that is very flexible and very robust. And so that's the Kuntsuya method. Yes?
You said you cannot.
Well, you can, but I don't know how to control the outcome.
No. You said you perturb your potential at one point, right? And did you know that there are, well, there is a sub-exponential decay or something? Is it not enough?
Yes, but
This will be a limit periodic potential.
no, I'm actually not claiming that it's impossible to do that. I'm only saying I don't know how to do it. So, but the point is the following. Yes, I mean, if you for almost every realization here, you will get these two solutions. But now to match them, you have to wiggle some random variable here.
Yes.
Yes, but if you just do that, you match the solution but kill limit periodicity. If you want to keep limit periodicity, you have to wiggle all.
Exactly my question. Why do you kill limit periodicity? You need the convergence only on.
No, but it's not periodic anymore. I mean,
it is not periodic, but you only because of the definition you have.
Yeah, so the V1 will not be periodic
Sorry.
anymore.
Yeah, I got it. Yeah.
No. So again, if someone shows me how to do this, I'll be happy because this is what I tried for a long time and couldn't do it. So.
No, I'm
No,
I just understood your
no, it's a natural thing to try, but I think it's technically not easy to implement. And so actually, so this Kuntsuya thing is.
Он не будет позитивным. Да. Okay. Sorry.
Just one thing. Couldn't you use the what's it called? Simon-Wolf criterion, which is at every step you can control it, no? I mean, when you are looking at this, right, you have some control of the resolvent.
Yeah.
Right, at every step of your procedure, or over large enough length scales. Couldn't you try to implement, because it doesn't carry.
Are you talking about the half line or the full line? So you.
The full line. I'm talking about the full line, but because this does not contain any trace of exponential decay. This criterion, right, just L2 convergence. So because you see the problem is with exponential localization is not what you're going to expect. You don't have exponential localization in this case, right? Because it's a play of scales. You're not even sure that you have sub-exponential decay, right? It's more natural to expect that you only have L2 convergence. So it would be natural to play convergence of the Green's function step by step and show that at such a large range, the Green's function do exactly what Simon-Wolf criterion tells them to do.
Okay,
right?
sounds very good.
I don't know. I mean,
I didn't try, so but I'm happy for any suggestion of how else one could do it. Yeah, so I mean, definitely, I mean, at this point, you do want to run through the various ways of, and so this is, so Kuntsuya, so actually, turned out to work in this case, and because it works, it gives you more. So the Kuntsuya method is really nice because, well, it has these various features. One feature is that it really doesn't care about identical distribution, so it just cares about independence, and that's really what I have here. So in this picture, I don't know if there's color chalk, the whole point is the following. These are good random variables, okay? But whatever I do here determines the values here, and I have to deal with them, they're there. But as soon as I've exhausted the good random variables at the first level, I will use the good random variables at the next level. So these are also good, okay? And then I will use these guys, okay? So these are the random variables I actually want to apply Kuntsuya to, and everything else in this picture will not be the random variables that participate in my localization proof, but they just present something I have to deal with, and I treat them as a background potential. Okay? So in particular, I have lots of random variables here, right? And all of them I treat as background potentials. So the Kuntsuya method is very convenient because it can deal with both things. It can deal with these varying distributions, so identical distribution is not necessary at all. They are independent, and it can deal very efficiently with background potentials, which are just here all over the place. So therefore, this is really what you should keep in mind. And as you see here, if you assume that you can deal with the background potential, really what you have is a random decaying model. Okay? You have a certain size of randomness up to here, randomness of smaller size here, randomness of yet smaller size here, and as you go to infinity, randomness goes to 0. It's a random decaying model plus some very complicated background potential. Okay? And so the Kuhn-Suyar method is very flexible in dealing with these things. Okay, so what does it do? So actually, let me just write down a theorem. That's probably easier. So let me write down one theorem. So given a linear functional, well, L from Rn to R, which is given by the sum of bj's xj's, j from 1 to n, set the norm, the plus norm of this functional, to be the sum of the absolute values of the bj's. So this is just notation, but I need that in the formulation of my theorem. So okay, so let Cn be independent random variables with distributions of the form Rn x dx, so absolutely continuous with density Rn, and the Rn's are just rescaled versions of the same distribution. So the Kuhn-Suyar method is more general, but we just work with these rescaled versions. It's good enough. So the rescaling parameters are called An, and R is compactly supported and bounded. Okay. So the theorem is long, that's why I'm writing it down. I mean, otherwise I can't discuss it. We have to look at something. Then there are d and lambda such that the following holds. So I fix them, and then the following statement is true. Assume An is bounded, and so now we have to be quantitative, right? So again, it's about an interplay between periods and sizes. So you can't just draw the picture and say I'm done. At some point you have to actually prove some estimates and see whether you get something. So the condition that comes out of the proof is the following. So in some sense, you can almost ignore the precise formulation, but I just want to tell you that there is something that comes naturally out of this Kuhn-Suyar method. So min A, this is the sine of n 2j squared A sine of n 2j minus 1 squared lambda. Okay, so this sum is finite. Okay, so this min here is in the exponent. So that's your assumption. That's what you need to eventually deduce, actually, that you have something that implies pure point spectrum. So let chi n be independent random variables that are uniformly bounded. Theorem doesn't end here, sorry. continues. I don't know where to, maybe, okay, so we will try to remember this definition of the norm. Okay, so, and this is the simple version of the theorem. This is not good enough to give that, but I'm starting with the simple version. So, uniformly bounded, let these LNs be linear functionals with uniformly bounded plus norms. Okay, so here finally then, almost surely here now is in the product space. Right, you have a bunch of random variables, you take the product of all, the x's, the chi's. Then, almost surely, the Schrödinger operator with potential. So here's my potential. Vn is psi n plus chi n plus ln of the vector psi minus absolute 1 plus 1 psi n minus 1. Has pure point spectrum. Okay, sorry about the length of the theorem. So it starts there, continues there, and ends here. The point is that you want to have a criterion for a pure point spectrum. The setup is that you have some random variables that are the good ones. Those are the ones that are colored in this picture. Then you have some random variables that describe background. And then you have these linear functionals that relate the value of your potential at n to the sites, well, strictly between n and minus n, or n and minus absolute n. Well, anyway, the other n. So, right? So that's the picture. There are three participants in the construction of V at n, say, right? So if you want to know what the potential does at this site here, well, there are lots of participants. Well, first of all, there are these theorems that allow you to start with anything you want. So this you put in the background potential into the chi. That's just fixed. Okay, so the chi's actually don't have to vary at all. They could be just fixed numbers, and then you regard them as Dirac masses at those numbers. So if you want to compute the potential at one site, there are three classes of participants. The first is, first of all, is all the background. What's the background? The background is the background potential that you start out with, and everything above the good level. That's background. The xi's are, sorry, that's not true. Is that true? That is true, yes. The xi's, so that's put in the chi's. The xi's are the boxed ones. And then the L's are these guys, right? So if you want to compute this value, you need this, this, and this, right? And so this here actually is just computed from the value here. So if you want to know what you have to add here to this value, you just compute n mod your first period and go to that site, look up the value that you produce there. It's one of the xi's for small n's, and that just goes there. So this is exactly the role of this thing. It tells you what contribution to n do the earlier xi's make, and based on the construction, it's just the xi that was determined earlier as I go inside out. Okay, so these are the three components, and the conclusion then is that almost surely you have pure point spectrum. So there's a version of this theorem that's a bit more complicated because it's adapted basically to this choice of scales and sizes. So here you just have, you don't see the periods here. So we have a version of this theorem that's a bit more elaborate with some adapted partitions that gives you basically something that applies to the limit periodic setting. But it will be such that all of the V's that we produce here are background plus limit periodic. So basically produce the guys that we want. And so if you want to prove these theorems, that's actually the interesting thing. So so I did actually try Kun-Suya maybe during this 5-year period where nothing worked. And I think I just didn't see how to implement these correlations here. But somehow in the end, when you see how to set things up so that the proof goes through relatively nicely, it's not that technical. I mean, you really just have to express these correlations between sites using these functionals. And so now once you have the setup, now you go into the proof of the original Kun-Suya localization proof. And in particular, there was a follow-up work by Simon looking at random decaying potentials based on Kun-Suya treatment. And so this is really what's going on here. So in some sense, this is sort of an evolution of Simon's treatment of random decaying potentials, because as you see, these colored boxes produce a random decaying potential. And so you want to exploit the random decaying nature. That's not decaying very fast, right? It can't decay too fast. That's clear. To control, say, the decay of eigenfunctions. So of course it's more complicated here because of this complicated background and the correlations, but once things are set up, you can try to run the Kun-Suya machine, and the nice thing is it actually works out exactly the same way. There is really one step where you have to check that these additional, so it was known in the Kun-Suya already that the background is okay. That was just known. So the new aspect here are the correlations. And so if you set up the machine, so I don't have time to go into that, and probably you don't want to see that. It's not pretty, but it's also in some sense elementary, so it's not that bad, but not something that you want to put on the blackboard. Then you notice that the only thing that changes is that when you compute the Jacobian of your change of variables, which is crucial to their method, the change disappears actually. You set things up, you include the change, you look at it, and it does nothing. Because you have to compute the determinant of a matrix, and the matrix, the new matrix, is the old matrix times one that obviously has determinant 1. And then you're very relieved, and you say, whoa, that's it, I'm done. So, so it was sort of a lucky coincidence that while we had to sort of make the framework more general, the old proof really worked. I mean, there were no sort of real major technical issues once you realize that this change just disappears once you set up the change of variables. Okay, so this version of the theorem gives you the quasi-periodic application, these small quasi-periodic potentials with possibly Liouville frequencies, and the limit periodic guys follow from some variation of that. With that, I will finish, and thank you very much.
Other questions or comments?
I presume the same construct works in high dimension as well, right?
No, Kun-Suya really is a one-dimensional method. Yeah, so I don't know. Well, I mean, you could.
I'm not talking
Oh, you mean the picture?
I'm talking about.
No, but you don't know localization for small randomness.
But in other words, you don't know.
Well, if you could prove localization of small coupling in 2 dimensions, you would be famous.
No, I mean, forget what's smallness. Let's say you take substantial potential and start to cook up things on that way.
Okay. No, but I mean, if you do it finitely many times, you get something periodic. If you do it infinitely many times, you need randomness to go to 0 to get convergence. And once it goes to 0, you need to understand what small random potentials do. And currently, we only do that in 1 dimension.
Other questions?
Well, you still know how the localization lengths behave.
You mean at the edges?
Yeah.
Okay. Yeah, you can. Yeah, I mean, you can work at the edges, but it's not clear whether. I mean, the edges shrink as you go through the. Right. I mean, because you really need information for the limit, but as you go through the approximants, the interval where you actually have statements shrinks. So it's not clear that you get anything in the limit. But yeah, no, I mean, it's certainly interesting to try to see what happens in higher dimensions if you sort of make these local random perturbations and make them periodic, as you can see. I don't know. I actually have no intuition.
I can see no further questions, so thank you very much again for a great lecture.